We're in section 7-5 in theorem 1. Theorem 1 says that if I'm lucky enough to have the Laplace transform of f of x to exist, if it's not, then I don't have to worry about theorem 1. Then the Laplace transform of the unit step function t minus a, f of t minus a, is going to equal e to the minus as, the Laplace transform of the f of t. Now, in order for this to work, a has to be greater than or equal to 0. It doesn't work if a is negative. And the Laplace transform has to exist. Okay, well, what the heck is the unit step function? All right, so unit step function goes like that, and at 0 I go up. And I go up to 1 because it's a unit. Okay, and if I have the unit step function of t minus a, then I end up having something that looks like this. And there's 1, there's a, and I end up going up to a and like that. So that's what a unit step function is, just in case we forgot. Now, theorem 2, one more thing. The Laplace transform of the unit step function t minus a, so all that guy, is going to be e to the minus as over s. Okay, and that's easily shown because so I got f of t is equal to 0 from 0 to t equal 5, and is 1 for t greater than or equal to 5. So that'd be a unit step function, and if I took the integral 0 to infinity of f of t e to the minus at, e to the minus s, yeah, e to the minus st, and then took that integral 0 to 5 of 0 plus integral 5 to infinity f of t, which is 1 e to the minus st, and I did that integral, I'd end up with having something that's e to the minus as over s. So that's how I end up getting that. Okay, well, there's a second theorem, theorem 2 in this section. And it says that if I have a periodic function, so I got something, a periodic function, I'm sine, I'm cosine, I'm sine, we've got some periodic function. Then the Laplace transform of that periodic function is going to be 1 over 1 minus e to the minus ps integral from 0 to p of e to the minus st, whatever the function is, dt, where p is the function of that periodic function. So those are the things to be considered. I don't think we use that in any of the problems we do. I'm not sure, but I don't think we do. Okay, look at some problems. Number 2, I have the f of s is equal to e to the minus s minus e to the minus 3s over s squared. And I'm supposed to find the inverse Laplace transform of that. And I see that I look at theorem 1, and I see that the inverse Laplace transform of e to the minus as f of s is equal to the unit step function t minus a and the function t minus a. Okay, well, if I look at the inverse Laplace transform of e to the minus s over s squared minus e to the minus 3s over s squared. So I'm looking at that, and I'm saying, well, what's the f of s? F of s is 1 over s squared. So f of t is going to be equal to t. And now I've got a unit step function that's going to say that that inverse Laplace transform is going to be u to the t minus a, which is a 1. There's a 1 sitting there. T minus 1, because the function is t, so it would be t minus 1. Minus, it's that minus sign sitting right there, unit step function t minus 3, the function t minus 3. So that's my final answer, and if I look at that and say, well, what the heck do I have here? Well, I have a function that goes up to 2, and 1 to 3, and I'm going to come over to 1, I'm going to come up to 3, and then I'm going to go that way. So that's what I'm going to end up looking like. Okay, I'm going to look at problem number 4. F of s is e to the minus s minus e to the 2 minus 2s divided by s minus 1. Okay, so I've got e to the minus s over s minus 1 minus e to the 2 minus 2 1 minus s over s minus 1. And I want the inverse Laplace transform of that. I see that the Laplace transform I'm dealing with is 1 over s minus 1. F of t turns out to be e to the t. So I look at it again and I say, well, the inverse Laplace transform of e to the minus s minus 1 is going to be a unit step function t minus 1, e to the t minus 1. And then I have left over this other thing over here, which I'm going to deal with separately, 2s over s minus 1. Okay, I look at that and I say, well, this is e to the 2 times e to the minus 2s. E to the 2 is just a constant, so this is going to be minus e to the 2 inverse Laplace transform e to the minus 2s over s squared s minus 1. Okay. That being the case, the Laplace transform is still 1 over s minus 1. F of t is still e to the t. So I'm going to have unit function t minus 1 from up above, e to the t minus 1, minus e squared, unit step function t minus 2, that is that 2 sitting there, e to the t. minus 1. And now we're supposed to draw that function out. And so I will do my best to do that. I probably should turn Maple on, have Maple turn it on for me. But okay, so I've got a 1, I've got a 5, I got a 10, I've got a 1, I have a 2. Okay, so that's all right. I'm gonna come in at 0. I pop up to 1. I have an exponential thing going into there. I drop down to 5, and I have an exponential looking thing going down like that. Okay, so much with drawing pictures. I'm doing number 6 next. F of s is s e to the minus s over s squared plus pi squared. I look at that and I see that I got a number 10 sitting there. Number 10 says cosine kt is equal to s over s squared plus k squared. Okay, so I'm going to look at the inverse Laplace transform of s e to the minus s divided by s squared plus pi squared. And I see that my f of s is s over s squared plus pi squared. So my f of t is going to be the cosine of pi t. Okay. And then I say, well, that means the inverse Laplace transform is going to be unit step function t minus 1. That's the minus 1 sitting right there. Cosine pi t minus 1. Okay, so that's what we have. And that's the final answer, in case anybody was wondering. Now we're supposed to have a graph, so I need to come out to a 1, and I'll put in a 1, a 2, a 3, a 4. Yeah, I might as well put it in a 5. We're going to go up to 1, we're going to go down to minus 1, and we're 0, we go up to 1, and this guy won't stop, so he keeps on going. And so he's a cosine function starting at 1 is what he basically is. Okay, so that was number 6. Going on to number 8. So f of s is s 1 minus e to the minus 2s divided by s squared plus pi squared. Okay, again, we see that we have s over s squared plus pi squared, which implies a cosine function, cosine of pi t. And so I've got the inverse Laplace transform of s over s squared plus pi squared minus the inverse Laplace transform. So that's the first guy, 1 times that. Inverse Laplace transform of s e to the minus 2s over s squared plus pi squared. Okay, so I've got, first guy is going to be cosine pi t, minus unit step function t minus 2 cosine pi t minus 2. And so that's the final answer sitting right there. And we're supposed to graph it. So we'll go and make a graph. And we're going to go up to 1. We're going to go down to minus 1. We're going to start at 1. We're going to go up to 2. And what color do I want? Okay, that'll be a good color. So I'm going to go down, back up. And then when I get to 2, I'm going to go straight down. Yeah, that looks bad. I'll do it in green. I go down, back up. I get to 2, straight down, 1 forever, 0 forever and ever. Okay, number 10. And I got f of s is equal to 2s e to the minus pi s minus e to the minus 2 pi s divided by s squared plus 4. Okay, so now I'm going to look at the inverse Laplace transform of 2s over s squared plus 4, and I'm going to see that that's going to be 2 cosine 2t from number 10 of the Laplace transform table again. So I'm looking at the inverse Laplace transform of 2s e to the minus pi s over s squared plus 4 minus the Laplace transform of 2s e to the minus 2 pi s over s squared plus 4. And I'm going to end up with unit step function t minus pi times 2 cosine 2 t minus pi minus unit step. So that's the first guy. That's that guy there. Unit step function t minus 2 pi 2 cosine 2 t minus 2 pi. And that's my final answer. And we have to graph it again. I don't know why we need to graph these things, but the author thinks that's important. 2 minus 2, I go to pi, I go up to 2 pi. Okay, so I'm 0, I get out to pi, I jump to 2. This is a cosine function, so I'm going to go down and back up. And when I get to 2 pi, I go straight down again, and I'm 0 forever and ever. And that is probably, if I ever redo these guys, I'll do the graphs using Maple. Have Maple draw the graphs for me. All right, number 12. I have f of t is equal to 1 when I'm between 1 and 4, and equals 0 when t is greater than 4. Okay, so I look at that and I say, well, if I look at the unit step function of t minus 1, I end up with a graph that looks like that. That's 1. And if I look at a unit step function of t minus 4, I end up with a graph that goes out to 4. And that looks like that. so now I say, well, what is the Laplace transform of u t minus 1 minus unit step function t minus 4? Because that's what we're looking at. And we'll put big brackets around that for, and I look at that and say, well, that's pretty simple. That's e to the minus s over s, because this is that guy. I have a unit guy sitting here. See this? 1 times 1 sitting there, times 1 sitting there, and the Laplace transform of that 1 is 1 over s, minus e to the minus 4s over s. Final answer. That's all there is, right? No more. Okay, now I'm going to do number 14. And I have f of t is going to be cosine pi t, 0 less than or equal to t less than or equal to 2. And it's going to be 0 for t greater than 2. Okay, so my function is going to be 1 minus the unit step function of t minus 2 cosine pi t is what it is. Okay, and I can rewrite that cosine pi t minus unit step function t minus 2 cosine pi t, and what I'm looking for is the Laplace transform of this function. So I'm going to look at what is the Laplace transform of that, and I'm going to have s over s squared plus pi squared minus e to the minus 2s, that's the 2 sitting right there, s over s squared plus pi squared, and that's my final answer. There's nothing else going on. Straight out of theorem 1. Looking at number 18, and I look at f of t is equal to cosine half pi t between 3 and 5, and is 0 and t is less than 3 and when t is greater than 5. Okay, so I look at that and I say, well, what the heck is that? Well, that's going to, my unit step functions, one goes to 3 and up, and the other one at 5, I'm going to go down, 3 and 5, and I'm just looking for something in there. Okay, well, that being the case, we can write this as unit step function t minus 3 minus unit step function t minus 5 times cosine 1/2 pi t. And what we want is the Laplace transform Okay, so I have a unit step function t minus 3 cosine 1/2 pi t minus unit step function t minus 5 cosine pi 1/2 pi t. And then I'm going to take the Laplace transform of unit step function t minus 3 sine pi over 2 t minus 3 minus unit step function t minus 5 sine pi over 2 t minus 5. Okay, so that's what I'm going to do. And I'm going to end up with e to the minus 3s, that's a 3, pi over 2 sine squared plus pi over 2 pi squared over 4 minus e to the minus 5s pi over 2 divided by s squared plus pi squared over 4 with checks with backup book. Okay, we're now going to do number 36. Okay, we have an electrical circuit. The inductor is 0. The resistor is 100 ohms. The capacitor is 10 to the minus 3rd farads. And we have a 100 for our voltage, 100 volts on our battery. And we're going to do something else. Let me read the problem for a moment. Okay, so the voltage is going to be 100 volts for the first 1 second. And then it's going to go to 0 if t is greater than 1 second. Okay, so I'm just going to have a 1 second of stuff there. So we get the equation out of the book, L d squared I dt squared plus R di dt plus 1 over ci is equal to the derivative of E. Okay, we find that L is 0, so this guy is 0. And we find that we're going to integrate the rest of these things. I'm going to integrate the rest of this stuff, and I'm going to do it between 0 and t, which in this case is going to be 1. Let's see if I can make a better integral sign. Integral that stuff. Integral this stuff. Okay, so I'm going to have Ri is equal to 1 over c integral 0 to t of I tau d tau is equal to e to the t. Okay, so that's what I've got. I'm going to write that 100i plus 1000 integral 0 to 1 I tau d tau is equal to 100 1 minus the unit step function t minus 1. Okay, so that gives me 100 for the first second, and then it goes away. All right, so that's what I've got. Now I'm going to take the Laplace transform of everything I see. Okay, so Laplace transform of everything I see, and I'm going to have um, 100 is plus 1000 is over s is equal to 100 over s minus 100 e to the minus s over s. e to the minus s over s. Okay, so that's what I have. I'm going to multiply everything through by s, so I get s off the bottom, and I get 100 s is plus 1000 is is equal to 10, 100. 100 minus 100 e to the minus s. Okay, and then I can solve for is. Is is equal to 100 minus 100 e to the minus s divided by 100s plus 1000. Okay, that seems like a reasonable thing to do. It looks like everything can be divided by 100, so I will do that. So is is equal to 1 minus e to the minus s divided by s plus 10. Okay, now I'm going to take the inverse Laplace transform of both sides, and I'm going to get I of t is the inverse Laplace transform of 1 over s plus 10 minus the inverse Laplace transform of e to the minus s over s plus 10. Okay, so I've got this, I think this is number 7. That's partially number 7. And I'm going to have e to the minus 10t minus unit step function t minus 1 e to the minus 10t. And that's my final answer. Final answer. And it checks with the back of the book. And with that, we are done with section 7-5.